y equals x squared, we should all know what that looks like. Parabola, we get points at 0, 1, 1, minus 1, 1. It looks something like that. Y equals 2 over x squared plus 1. It's kind of like a bell curve shape. When we plug in 0 for x, we get 2 over 1. If we plug in 1 for x, we get 1. If we plug in minus 1 for x, we get 1 for y. So we end up with something that looks like this. Right, by inspection, you should be able to tell that the limit as x goes to either plus or minus infinity for 2 over x squared plus 1 is equal to 0, right? Because the bottom's getting really big, the top is constant. Anyway, not super important. What's important is just being able to tell which graph is on top and which graph is underneath. So we've clearly got 2 over x squared plus 1 here, y equals x squared here. The region bounded between them is pretty obvious, and in particular there's no ambiguity. All the other regions that you see determined by these curves, like all this stuff down here, this stuff in between, this stuff in between, this stuff out here, those are all open regions. So there's no ambiguity as to which region is the region enclosed between the two. Now, like the previous problem that we talked about, the intersections are pretty obvious here. Just by plotting a couple points we could find them, but it's important to have a more systematic way of figuring out what those intersections are. And that systematic way of doing it is set the two equations equal to each other. So set y equals x squared equal to y equals 2 over x squared plus 1 and solve. All right, so how do you solve? You can multiply the x squared to the other side, so you get x to the 4th plus x squared equals 2. Now notice if I bring the 2 to the other side, it's kind of like a quadratic equation, except it's x to the 4th and x squared, right? So this is still the square of this term, right? And so we can factor this. We can factor it as x squared plus 2, x squared minus 1 is equal to 0, right? Same as solving a quadratic. Now, the thing to notice is if you try to set x squared equal to negative 2, right, to get the solution for this first term, there is no solution to this, right? Because you can't square a number and get negative 2. But we can solve for x squared is equal to 1. We get x is equal to plus or minus 1, right? And that's exactly what we'd expect based on our graph and the points that we plotted. At this point, we're really ready to integrate. We can see on our masterpiece of a graph here the region that we're trying to find the area of. And notice also that it's clear that that's the only region bounded by the graphs of x squared and 2 over x squared plus 1, right? So both of these curves split the xy plane up into a bunch of regions, right? You've got all this region down here, this one over here, this one to the left, this one in between up top, but this is the only region that's truly bounded by two curves, right? Now from the work we did on the previous slide, that region starts at negative 1, ends at x equals 1, and has a clear upper boundary and lower boundary, right? So we're ready to set up. Our area is going to be given by the integral from negative 1 to 1 of, well, whatever's on top, in this case 2 over x squared plus 1, minus whatever's on the bottom, in this case x squared. And we're integrating all of that with respect to x. One thing we could do to make life even easier is to notice that both 2 over x squared plus 1 and x squared have perfect symmetry about the y-axis. Right? So this stuff on the right is exactly the same as all the stuff on the left in terms of area. So why not say that this is going to be twice the integral from 0 to 1 of all the same stuff. Right? And the advantage to that is that typically plugging in 0 means things are going to cancel out and just makes the arithmetic at the end a little bit easier. Okay, let's take some antiderivatives and see what happens. Antiderivative of 1 over x squared plus 1 is tan inverse, or arctan, so I'm going to get 2 tan inverse of x. And the antiderivative of x squared is x cubed over 3, plugging in 0, plugging in 1, and subtracting. Okay, so we get some nice cancellation, right? You plug in 0 here, you get 0. Plug in 0 to tan inverse. Well, tangent of 0 is 0, so that's also going to disappear. And then in the first set of parentheses, we get 2 times pi over 4 minus 1 over 3. Right? That's not so bad. Just distribute, simplify, so we get 4 pi over 4 minus 2 over 3. 4's cancel, leaves us with pi minus 2/3.